We are starting section 5.4 in this video, and this is on the Fundamental Theorem of Calculus. So you know it's got to be kind of a big deal. There are two parts to this theorem, part 1 and part 2, and we will work our way through both of these. As a little intro to part 1, we are going to consider the idea of an area function, f of x. This is going to give the area under the curve y equals f of t from t equals a to t equals x. Okay, now notice that it's a little different variable-wise from what we usually do. This is not y equals f of x, it's f of t. And x is actually one of our endpoints of the interval that we're looking at. So if we want the area under this curve from t equals a to t equals x, that is actually going to be an integral like we've seen in the past couple sections. So our function, f of x, is going to be the integral from a to x of little f of t dt. Okay, so t is the variable inside the integral. It's our variable of integration. We're doing things with respect to t in there. But the overall area function f of x is a function of x, our upper limit of integration. So there's kind of some different things going on here. Let's look at this in the context of an example. So we're going to consider f of t equals 1/2 t and use a equals 2 in this f of x function. So our area function that we're looking at, f of x, would look like this. The integral from, a, which is 2, so 2 to x of f of t, which is 1/2 t dt. All right. Now, before we do anything with that, Riemann sum wise or anything along those lines, let's try to evaluate this one geometrically by looking at the area as a geometry formula. And we can do this because our function is just a little line, 1/2 t. So let's set up some axes here. Okay. And put in our line slope of 1/2, intercept of 0. Okay. So that is what our function looks like. F of t equals 1/2 t. All right, so there's t, and then y equals f of t. All right, so our area function is taking the area beneath that curve from 2 to some point, some upper limit x. And I'm going to try and keep this as generic as I can. I'm just going to put x like out here. And note that for our area function, x is a variable. So this x is going to be able to move around. It varies. So this is movable. You could draw x out further this way. You could move x in. That is going to affect the amount of area that we get from this integral or from this area function, as it's the area underneath the curve here. So changing that upper limit is definitely going to have an effect. But overall, what we're looking at here between the f of t equals 1/2 t, between that and the t-axis, is essentially a trapezoid. So we can calculate this by finding the area of a trapezoid, which, if it's been a while since you took geometry, you might not remember this one. That's okay. We're going to go over the formula here. we've essentially got a trapezoid like this. Okay, if you kind of tilt your head to the side and look at that green area. All right. The area formula for a trapezoid depends on the height of the trapezoid for sure. And also the two bases, the horizontal sides drawn here, base 1 and base 2. Okay. So area of a trapezoid formula is that A equals base 1 plus base 2 divided by 2. So you like average out your base lengths and then multiply by the height. Okay, so that's the area of a trapezoid, little refresher. And here in our picture, we can find what those bases and that height would be. So here, base 1 would be this little guy right here. All right, getting that top base there. The length of that base, since this one is set, this is the 0.2 there, our A value, the length of that base is just 1 unit. So B1 equals 1. And B2 is the one that can change. That's our longer base in the picture here. So that would correspond to this guy on our sketch. And that is going to change depending on where X has moved to. So the length of this, or the height set there, is just going to be f of x, depending wherever x is. This, by the way, is f of 2. Okay. But f of x, whatever x is, it's just going to be 1/2 x. And then our height h, that's this side, that's going to equate to this portion along the t-axis here. So if we want to find out the length of that, we would take x minus 2, the difference between our endpoints there. X minus 2. Okay. And so our area here, finding this in geometric terms, from that formula, is going to be A equals B1 plus B2 over H, or sorry, over 2 times H. There we go. All right, stick in the B1, which is 1 plus 1/2 X for B2, divide by 2, and multiply by H, which is X minus 2. And let's simplify this. We definitely can here. Okay, so we would get A equals, let's get a common denominator up there. That'd be 2 plus x over 2 for these terms right here, because that's 1 plus x over 2. So getting the common denominator brings you to this stage. Okay, and that's still being divided by 2 times x minus 2. And then let's switch that up a little bit. 1/2 times 2 plus x over 2 times x minus 2. That would be, I'm going to rewrite this guy right here as x plus 2 over 4 times x minus 2. Okay, because then I've got that nice difference of squares thing on top there, x plus 2 times x minus 2. That's going to be x squared minus 4 all over 4. And to split that up just a little bit here, let's do some division. That would give us 1/4 x squared minus 1. Okay, so that finds the area beneath our function, beneath our curve here, from 2 to x. Okay, But we know that this is also expressed by the area function involving the integral. So f of x also equals this. F of x is that area function 2 to x, 1/2 t dt. But that area function is just finding the area, okay? And that's what we found here with this 1/4 x squared minus 1. So if you wanted to find the area under this line or this function's graph, function's curve, from 2 to any point x, you wouldn't have to repeat this geometric process. You wouldn't necessarily have to do a Riemann sum if you had already computed this 1/4 x squared minus 1. You could just plug in whatever your x value is, and then you'd know the area under the curve. Now, that's not really so much what we're going to focus on here in the Fundamental Theorem Part 1. We're going to focus a lot on this little note to follow here. What happens if we take the derivative of this area function, f prime of x, or if you prefer, you could think of this as d dx of big F of x. All right. That would be the derivative of 1/4 x squared minus 1. And so that would give us 2 over 4 x to the first minus 0. All right, we know our power rule by now. And so that would be 1/2 x. Now, notice what our original function was again that we were focusing on for the area. It was right up here. F of t equals 1/2 t. Down here we have 1/2 x. So that is literally just our function f of t, but you've plugged x into it. So this is little f of x. All right. And it turns out that regardless of which function you start with here, whatever your f of t is, if you go through this process of finding the area formula, this area function, if you then take its derivative with respect to x, you'll always end up with f of x, little f of x, coming back to you. The derivative with respect to x of big F of x is going to be little f of x. This is not a coincidence. Nope. So this will work, okay, for a lot more functions than what we just saw. It's not just something unique to f of t equals 1/2 t. So kind of interesting. Okay, so we'll reveal what's going on here in the next video.